Good afternoon, everybody. I'm pleased to introduce the speech of Professor Tibor Hortobagyi. It's really a pleasure and an honor to receive him. And Professor Hortobagyi is Hungarian. He had all the scientific formation education in the United States. And in the last 4 years, he's working in the University of Groningen, the Medical School of Groningen, North Holland, as I think he's showing to us more precisely in a few minutes. And more than the converging interests in research teams, I think that what brought Tibor here to contact me was the experience of my daughter at the University of Groningen. After summer school, she returned for a 1-year internship studying cancer research. And from this period, it was established a sound collaboration between the Medical School of Groningen and the Medical School of the University of São Paulo. It has become a very productive collaboration because from this event, it was established a collaboration with scientific projects and something important for today. Many students going from Brazil, from the University of São Paulo, from the medical school in particular, to the medical school of Groningen. Very many students after my daughter experience, successful experience. And I think, I suspect that the intention of Tibor is doing something similar for human movement science. He works in the border of neurophysiology and biomechanics, or the combination of both. And he's here to present some of the current projects and the future projects, exactly to attract, to prospect collaborations with researchers and attracting students to Groningen, maybe to reproduce, to extend the experience, which has been done through Science of Borders or Ciências Sem Fronteiras. Nowadays, not so with not so much money, but it is still possible. It is still upright. It's possible to use these programs or other programs to promote this cooperation. And Professor Tibor is going to present this work here. And based on this, I would highlight that this is a different speech from that we are used to attend, because not to understand and to learn from Dr. Tibor's experience and work, but to prospect possible collaborations, future work. In this sense, I would draw your attention to this point. So another important point is that Professor Tibor is staying in São Paulo for a very short period, just today and departing tomorrow. So pay deep attention to his work, his words, because we have not long time to promote this experience and to take advantage of this visit. In this same direction, following Professor Tibor's presentation, Andrea Lima-Pardini, nowadays postdoc in the neurology department of the medical school of the University of São Paulo, will present a project intended to be developed with Professor Tibor. And to close the session, Professor André Kohn we will present some work, some projects with the same purpose, potentially attracting collaboration and prospecting other people to work together. So from this introduction, I pass the word to Professor Tibor. He started the speech. Professor Tibor, be welcome.
Thank you very much. It is a great pleasure to be here, and I say just a wave to the viewers, because I will step out the view so the slides can be seen better. I'm not that important. I'm not a pretty view, so might as well look at the slides. So I would like to thank everyone for coming and giving this opportunity. And as you can see from the slide here already, I am trying to bring together two continents as much as possible. And I would like to extend special thanks to Luis for arranging this meeting to become possible. And also would like to thank the graduate school there for giving a minimum amount of funds for this visit. And I am supposed to give a small token of appreciation, a gift to Luis right at this moment, but I can do it only virtually because I left it in the hotel. So later on, we go back to the hotel and you will get your gift. And I apologize for the oversight. But just enjoy it, okay? So this is what's called the Delft blue, which is a city in the Netherlands. And they developed this special color of blue. And these are very, very popular and very famous China to drink your Brazilian coffee from, or tea. So I wanted to show you a slide, a short video that was taken at the Mayo Clinic of Successful Aging, because the theme of today's presentation is about aging. And I'm not sure if I have to press this button here or what button. And this was taken at the Mayo. There's supposed to be sound here too. And I think this video shows very elegantly successful aging. You see broadcasting, and you see balance control, and you will see a fall. This is in the lobby in the Mayo Clinic in America. It's a 92-year-old couple. And they are educating the patients in the hospital in the lobby. So I guess I can show a target for you, what we are aiming for ultimately, and then good luck. So as Luis very correctly and succinctly expressed this idea that somebody is calling somebody, that there is a big push for collaboration, international collaboration. And there is what's called a structural agreement. I'm not sure you can follow these words because I cannot. It's a structural agreement between institutions and government to create sandwich PhDs, as it is called, where there is a dual degree given. And also some opportunities for postdocs that we will maybe hear about later. So, and this is particularly about providing opportunities for Brazilian students to receive international training, and also for the faculty, like I am here, faculty, to exchange ideas. And in the morning we have already discussed the projects ongoing in the lab here. And there are some links here. And if anybody would like to have the slides, I can print a PDF and just distribute it. And of course, as you saw it, there are 2 tracks in this program, the PhD and the postdocs. I just point out then down here on the slides, I have the slide number if you have a specific question, and also the viewers, maybe, I'm not sure you can see it, but there is a slide number. Maybe it's easier to ask questions about specific slides. And so the idea is that here a student and the professor start talking about a specific theme, a topic, and then these themes are somehow interchanged between the 2 partners, and then create a sandwich where the poor student is pressed between these two continents, and there will be a 2 + 2 or a 4, even a 4-year program according to the guidelines. So, well, this is how it looks in cartoon, the idea. And why is this a good idea? Of course, you would ask immediately. I can tell you I have a slide at the end, maybe. Yeah, I think I put it in. I am collaborating with many people in Europe and in the United States and in Japan and other places. It is really important, and it's a good idea to exchange views. You get out your box, you take your hat off, you open up your brains to other people's ideas. So this is not just some sort of a governmental statement, like a slogan on a flag or something, but I really mean it, because on a daily basis. We just finished the review that was published. I just mentioned it to you. So there was a person from Germany, there was one from Switzerland, and there was one from America, and there was one, a couple of us from the Netherlands. So, I mean, I could have never produced a paper like that without these people coming in and having their reviews and corrections and edits on this paper. And so this is truly what I mean by this. And there are some other factors here, but I wanted to really emphasize this first one, and there are some other factors here that you can see. And of course, this is not for everyone, this kind of program. There is a need for a higher level training and preparation even before. So these are the ideal candidate for this program would be a person with some sort of master's degree in science, biology, or kinesiology, or along those areas, strong academics, high grades, very high motivation to be able to do the work, and also do some work potentially, in a strange environment, in a new environment, which can be inhibiting some people and could be motivating further others. It's very important to be able to communicate, of course, in English. Having some computational skills these days is almost impossible to live without it. And some other features that this person should have, and we would ideally like to have it. And so I don't want to go too much on the administrative side, but technically what the guidelines are saying is that there would be a PhD awarded in the Netherlands, and there would be a PhD also awarded here, and this would be the dual degree, what is called, presumably. So, and there are team members, and each team has its own members, and then try to train this person to become a good scientist. So the environment, of course, there would be the Brazilian part here that you are all very well aware of and familiar with, but you may know a little bit less about the other side, in a country quite far away from here in north, and not as warm as Sao Paulo today, 26, 7, and 8. And you can see Amsterdam is where you would be flying in probably to, or the student would be flying into, and then you would have to take a train for a little while to Groningen up in the north here, and this is Germany here, and this is Belgium. And this town that Louis was lucky to visit, I suppose, and his daughter is still there, has all kinds of art and history. This is the the building from, I try not to exaggerate, I think it's from 1576, actually quite similar to the building that I saw yesterday. Right, that was about 1550s. The first building in Sao Paulo. The name I don't remember exactly. So there are some very, and then there is modern art. This is in every textbook. This is the Modern Museum of Art in Groningen. Of course, the Netherlands is, as you know, 60% of the country is below water. So there are a lot of canals and water and stuff. And then there are some beautiful areas there. In the springtime is particularly nice. The winter is not as nice. So, but with global warming, things are changing, I must say, because last year I didn't have my gloves on one time, the whole winter. Yes. So this is the medical center. This is the hospital. And they try to make patients very comfortable. And you can see it's a closed roof here, and they have a waterfall Christmas time decorated with special lighting. And then this university is about 400 years old. Well, it was last year in June when the celebrations took place. The whole town was turned upside down, as you can imagine. And this is the academy building, as they call it. This is where, in this room here, in this big room here, is where the PhD promotions take, as they call them, promotions. The PhD is awarded, and so that's a very ceremonial process. And there are, of course, all kinds of bicycles there, which is the bicycle capital of the world. So I don't own an automobile anymore. I walk and ride a bicycle there. So that's pretty standard. And then getting closer to the department, you can see here the animal facility next to the medical school. This is the medical school. Here are some classrooms in this gold building. And you can see the medicine, dentistry, pharmacy, and this horrible word here, bewegingswetenskappen, is the word for kinesiology. So these, yeah, I know. So these are the four units that are within this faculty or block, and of course we are one of them. And I don't know what happened to this slide here, but something happened to it. And just very briefly about the department, it has 3 units: rehabilitation, sport, and aging. And I am of course in this aging, that's why it's red. And there are research priorities that our director boards identified: perceptual motor mechanisms underpinning gait balance and fall prevention, and it goes across these 3 domains, themes. And then there are other areas, physical activity and cognition. So we do quite a bit of work on effects of physical activity on mild cognitive impairment and dementia and other characteristics of performance. This is mostly in the sport area, but as you know, that sport can be used as a tool, as a vehicle in aging also. Optimization, functional recovery, and motor learning development, and neuromuscular control. So these are the main priorities and research that is going on in the department across these themes, as we call them. And there are about, depending on how you count, 45, 50, so it's quite similar size, 45, 50 people in the department, teachers, and 12 PIs. And we have various kinds of funding and all kinds of other, I just mentioned one here. This is the dementia program that got funded. So aging seems to be quite popular these days. I mean, it's not popular for us to get old. We don't like that part, but there are many people writing about aging every day, okay? And I am trying to find in this maze one particular one, but because I rearranged this because there were new ones. Oh, this one here. So this ending aging. So there are some pretty dramatic calls, and this guy is the editor of listen to the name of this journal, Rejuvenation Research. Okay? That's the name of this journal. And he's the editor of that. And I saw him presenting Groningen, and he just says that aging is a medical condition. So it's curable. You're hearing me. So you go to the websites of sense.org, which is out in California, and they have $1 million of funding about this program, how through biological means actually aging can be cured. You're hearing me correctly. So you can, Aubrey, the Gray is his name. I can give you the website and everything. And they are very serious about these 7 lines of work, cellular, molecular biology work, that will end aging. So the last time he spoke in Groningen, he stated that Parkinson's disease will be cured in about 5 years. You heard me. This is what he says. So there are some very serious people in here that we can take seriously or not. So getting closer to home, in our department we have, as you can see, 6 individuals who do work in aging area: perception, action, physical activity and cognition, neuroscience of motor aging, clinical function, gait control and falls, and upper extremity function. I will speak about these 2 individuals later, and I show a few of the ideas that I am representing. And we collaborate, as I mentioned, locally, nationally, and internationally. Truly, we have all kinds of connections, so it would be a very rich environment for any student or anyone come over and get submerged in this environment. And I am supervising currently 12 PhD students in the program. So as you can imagine, this is no small feat to administer a program with 12 students at this level. And the program is 4 years old, as you suspect. And we have all kinds of various measurements. I have the photos of some of them because the rest of them were lazy to send me a picture. So I have only the 5 of them shown here. And these thesis work consist of those themes that I just showed it to you a minute ago. So I show you just a couple of ideas. As Luis very correctly presented out, I am not showing virtually any data from previous studies because you can read all those. You typed in the names and you have the articles. But rather just a little bit of a brainstorming about possibilities. So this morning I saw the current ongoing work with pilot data, preliminary data, and I will show some data, not much data, which is unusual for me, but that's what it is. So we are doing quite a bit of work on this hypothesis that the central nervous system dysfunction is really underlies the age-related decline in motor control. So the key thing that we are thinking is that there is muscle weakness, there is atrophy, there is this and there is that. But really we think that the neural output that comes from the segmental level and the brain is somehow suboptimal, and that is what's causing motor aberrations, motor dysfunction. And my lab and in collaboration with others, examine this idea in manual tasks and also in postural tasks. So we look at the top and we look at the bottom of this phenomena. And we are doing work now, and we are planning, designing, as you will see in a moment, studies about understanding the plasticity, this dysfunction, how far this dysfunction can be pushed with task complexity, with priming for those who are not responding well. And then, of course, we are interested in your ideas. In the postural work, this is task difficulty, again, complexity, difficulty. We have plans for manipulating the base of support and performing the balance training in that sense. And see the plasticity of the lower extremity system in relation to balance control. I will show a couple ideas that still preliminary as a potential basis for discussion. We are doing some work now, also have pilot data in a few subjects that I show you. The neural control of anticipatory postural control. So we do peripheral nerve stimulation and brain stimulation to look at how is the brain preparing or not preparing for self-perturbed conditions. And I will not read all these things. As I mentioned it to you, I can distribute the slides. I can give you the slides, and we can discuss some of these ideas. But these are just spelled out into projects, actually, that we are planning to do. And the principles that goes through this slide here is really we try to correlate the neural and the behavioral outcomes. So as opposed to just taking an isolated measurement on a specific physiological outcome, we are really, really very keen on seeing the functional meaning of these measurements. And I will not, well, maybe some of you will be surprised, but so there is about 12 papers now these days in motor learning and aging and using magnetic brain stimulation. And guess what is the correlation between the outcome of the magnetic brain stimulation evoked responses, the motor evoked potential, and the motor learning? So you do this silly task with your hand or, you know, whatever, your finger, 300 times, and you improve like crazy. You have 300% in Carson's study and other studies of improvement in motor learning. And then you stimulate the brain with this thing. You will see a slide later. And what do you think is the association between the learning and the evoked responses in the TMS? The change in the magnitude of the amplitude. What is the correlation? Well, you guessed it right, 0. So we try to understand more of a holistic, more of a mechanistic way of multiple measures approaching like a Christmas tree, dressing up the Christmas tree, ornamenting it, as opposed to taking single individual measures, because it seems that it's not working too well. So those days are over when we do a single measurement and a single behavior, and we try to understand the behavior. It will not explain the behavior. So I would like to show you how we try to merge these ideas to postural control from the manual one. So what we plan to do is, these are 2 videos here, if I can get to it, to click on it. And so we do this visual motor task. If it works, it works. So maybe you can see the person is moving the hand, and the goal is to match the target. As you can see, this is a very simple task. So the person, a young, healthy person, I do it one more time, can do this task really easily. So what is this? Extension up, wrist, this is the wrist, and flexion down. And we measure the error, that's the behavior. And we do this practice, and we increase the complexity in young and old people to determine the effect of complexity. And the way we increase the complexity, that we quantify the number of turns, the number of change direction, and the rate. So we can quantitate actually the learning task, the template itself, how complicated it is or not, and then we associate that with the learning, the behavior. And then this is in the postural. This is in the postural situation where we have right now just a line, but we will plan to adapt, as we'll see in the next slide, a pretty complicated and very challenging task to do motor learning of balance. So we are working on this idea that how we can incorporate motor learning principles into balance training and improve this paradigm. So this is what I just told you, and as you can see from this list, which I am not detailing here to all the measurements, we plan to measure the behavior, as I illustrated to you, as the difference, the error between, for example, center of pressure and the target, or with the hand, with the flexion, extension, with the elbow. We are doing this with the shoulder and the wrist, so various joints. And so that would be the behavioral outcome. And we would measure the mechanics with center of pressure and also kinematics, meaning that how we can quantify, as you see, the strategy change during these behaviors and how these strategy changes actually explain the behavior. And several neural metrics, which is various kinds of stimulations and EMG outcomes. And we are becoming very, very interested in this paradigm in terms of the weight shift through visual motor practice. So what I showed you, the following the line and constantly changing weight shift all the time, and both direct X and Y, so anterior, posterior, and medial lateral. So so here you can see a template that it is very complex to produce for you to follow this with weight shift is very difficult. All the adults in the first 10 minutes are not able to do this task. It is so difficult. So there's a huge learning. And so it can be 3 seconds long, it can be whatever seconds long, and 2 seconds and 1 second. So the rate, this thing can go fast and slow and sideways and forward. It's pretty challenging, and you will see that we are designing even more challenging tasks, which I'm showing here. So we are planning to do weight shift exercises actually on one leg. On firm, something is missing here. Yeah. Something is missing here, but it's not coming through my picture. But so we try to do, well, I'm showing just 2 pictures of this intensity. So it's a big difficulty in balance training and postural control training, the intensity issue. And we try to come up with some ideas here. I'm not sure it's working. So here you have the screen. This will be on the screen. And the person will have to shift the weight or do anything with the arm to follow this pattern, which is projected for her in front of on the screen. And of course, this is a force platform, and then you can do this standing on a very unstable. So this is a stable surface, and this is an unstable surface, and you can imagine the permutations, that the kinds of things we can do here endlessly. But I'm not showing all those. How we can manipulate the intensity. And so during these tasks, we would have markers, so motion analysis system monitoring this person, and we would measure the forces, and we could actually compute the angular momentum around the joints. So we would have what is the angular momentum, the rotational quantity of movement at the ankle, the knee, the free limb, the hip, and the shoulder and the head, and even the arms. And based on this, reconstruct this idea and challenge this thing, what is called the hip strategy and ankle strategy. So we are after this idea to determine that, actually refute the hip strategy, because we think most of it is actually happening at the ankle. And those who cannot do it at the ankle will shift to the hip. So that's where the personalization and the individualization might come into place, because some people can do this way, some people can do that way. So we will see. So this is what we are working on. This is a pretty complex paradigm, but I think it's very fruitful because it approaches from multiple angles and through a challenging task. So we plan to do this. I give you just one slice of this whole concept here that we are working on a big ranked application with this. Is this reweighting or motor strategy. So this morning we heard about this, so we are speaking totally the same language. At the beginning of the study, we would look at the age by surface by sensory weighting interaction. Well, how we do this? Well, traditionally the sensory weighting was determined. Any students remember how this is done in posture work? We check the students on this. How is the sensory weighting tested? It was tested in the 1960s, 70s originally. What did people stand on? You remember? From foam and eyes closed and eyes open. We think that's a good paradigm, but we plan to improve on this so that we actually create an optic flow for the visual component and a galvanic stimulation for the vestibular component, so we can really quantify these elements more accurately, and the presence and withdrawal of these stimuli would leave the net effect of proprioception, which we are not measuring, because that's a little bit too tough to measure. So the idea would be in this project, what did I do? I did this, okay. So that there would be a motor learning training according to the paradigm I just showed you. At the pre-training level, we would assess what is the effect of these perturbations, non-optic galvanic, on a stable and on the unstable. Well, we can change this to two-legged and this legged and whatever. And then we could characterize this individual. How is this person actually balancing, and how he or she is responding to, well, a little bit more real life type of sensory perturbation. And the weighting would be determined, as you see, maybe in a button further down there. How the EMG, the central pressure, and the angular momentum measured during optic flow and galvanic perturbations or none would be affected. And based on that, we could see the strategy, whether they go to the hip, they go to the ankle, or whatever they are doing. So we can isolate that, we can extract that information maybe for the first time really effectively. And then they would be undergoing short-term exercise training with the paradigm I just showed you, and then we would test them after the fact again and see what's going on. And then, of course, this can be done over a longer period of time, but I'm not showing all that. I'm trying. That was slide 26. I will not read this slide, but we plan to do various other types of measurements in response to this type of balance training, where we look at the proactive, reactive balance and gait stability and gait variability. So that's what Claudine Lamos, the woman who is, slides are coming in a minute, would come in. And we are still examining various magnetic brain stimulation, muscle synergy measures, jaw coordination. So this is the younger man that I show, Alessio Murgia. He's very keen on computing the interjoint coordination as a measure of adaptation. So we have several other ideas about this area, and I show just a picture that how this is done with TMS. We use a special coil in this experiment. We still use the eyes open, the eyes closed on the foam, and eyes open, and we can measure, we can quantify the motor evoked potentials in young and old individuals, and correlate that, I'm not showing all the slides, correlate that with behavior, and we found indeed that the inhibition, the inability to regulate the inhibition in the motor cortex is actually associated with the behavior under these conditions. So we try to relate the behavior to the outcomes. I guess I better point. We are doing another type of paradigm now, and with Wolfgang Taube in Switzerland and Greg Tokono in Canada, I am working on this project, and we are interested in the anticipatory postural adjustment. So if you stand here and you tell me to swing my arm, swing my arm. I do this. You don't see it, but there is a minute, very small amount of adjustment taking place in the center of mass, because I am displacing through the movement, through the acceleration, and by the weight distribution. So there is a center of mass goes momentarily forward and then comes back. So there is a self-perturbation. We are very keen on understanding this when an old lady reaches up for a cup in the cupboard. What is actually happening in the brain before she reaches? So that's the anticipatory. So we are doing studies on this now with peripheral nerve stimulation, examining various responses to that, and also with brain stimulation, what is the preparatory state of the brain and the segmental pathways in anticipation of a self-perturbation. So here you can see the paradigm we are using right now. We give a warning signal, and then we give a go signal varying between 1-2 seconds, and then we give stimulation either at the nerve down at the leg or to the brain at the head at different intervals preceding the reaction. So we are able to time these measurements so that they actually occur before the movement. Okay? And as you can see in one particular example, so here is the arm this is the arm acceleration. This is a little bit of a jerkiness on the leg, and this is the H reflex evoked in the soleus, and this is the anterior deltoid corresponding to that. So here you can see the electromechanical delay, and here is the movement onset, the arm swinging, and then we plot it, and we can see that here is the movement onset. There is a large depression relative to control. My slides are not coming through with this, somehow. There is a line here and all this, whatever. So that 100%, there is a line here. You can see this large depression here, particularly around 20 milliseconds in this particular one subject. This is one subject in preparation for the arm swing. So we are examining the mechanisms of this preparatory state in young and old people, and this is the H reflex study, and then we have the magnetic brain stimulation. This looks pretty simple, but this is not that simple. We've been working on this for 3 months now to setting it up. It's very difficult. For those of you may not seen this magnetic brain stimulation, I said this now about 20 times, and you still don't know what I'm talking about. So I thought maybe I'll put a few slides in here about brain stimulation. So here I'm using a small coil from the early days when I worked at the National Institutes of Health in America, in Bethesda. This is a custom-made small coil, and we put it on the head, and it creates a magnetic field, and the magnetic field penetrates the skull. And the magnetic field then depolarizes the excitable cells underneath. And so here you can see this, one of my master students, that we can record from the FDI, so first dorsal interosseous, or the biceps, or whatever muscle. And then we have a motor evoked potential on the screen. This is in the FDI. This is a big amplitude. This is 1, 2, 3, 4 millivolts. So it's a big, and response is much smaller in the biceps. And then we can examine with this technique, particularly if we interconnect two stimulators, we can particularly examine, so this is the supplementary motor area, this is the motor area M1. We can examine pathways that are inhibitory and excitatory, so SICS, short interval cortical inhibition, and long intracortical inhibition. We can identify particularly GABAergic horizontal connections, the excitability of these pathways using the double pulse experiments, and correlate hopefully these measures with behavior under these conditions that I mentioned to you. So this will be the corticospinal excitability going to the other side, and there are all kinds of inputs that go on this and modulate that output. So this is a healthy aging slide again. This is in Vancouver, just a few kilometers north from here. And I took this photo. I'm not showing you the video. I have a video of this lady. She's 91 years old. I talked to her, and she came across the Capilano suspension bridge, which sways over 200 meters of a canyon. So you look down, it's like, wow. And then you step, and it does this to you. She came across back and forth. So I have a video of her, but I forgot to load that because it's easier to explain it. So she's going in front of me, and she's holding on, and she goes across and back. Can you imagine the challenge? So I cannot show a better picture in the context of balance, dynamic balance. There's somebody coming across at age 90, the Capilano suspension bridge, 200 meters above ground. So the theme too, and I am finishing slowly, is by this young fellow. He's an engineer, a mechanical engineer, and he and I am also very interested in upper extremity shoulder function. About 20% of us getting older have difficulty raising our arms, particularly the shoulder area. At least that's what the statistics is in the Netherlands. It's a high number. And of course, when you cannot use your arm, that becomes a problem. So we are interested in this. He is in this particular project using musculoskeletal modeling and estimating individual muscle forces based on the SIM, another model, in normal individuals, the backlines, and shoulder muscular dystrophy, which is a very good but very sad model for shoulder function, because these people cannot really lift their arms. And you have to use various kinds of supportive devices. And we try to understand what does the brain do to the activation of these muscles when there is support. There is a little bit less support, a little bit more support in this kind of people, in weak people, and so those kind of things. So this project is in upper extremity. If anybody works here in this department or someone would pick up on it, this would be an upper extremity. Here you can see some of the testing that we are doing. We are measuring the arm weight, and we are using kinematic analysis about reaching movement and shoulder function. And based on these tests, we can model the shoulder and compute individual muscle forces. So determine the mechanical and neural mechanisms of shoulder function with increasing arm support and arm weight of the arm weight, and model individual forces. So in the further in this project, we take measurements on a dynamometer that maybe you also have here, a King Cobra Biodex dynamometer. You might have heard about it. And we measure the arm weight, we measure the muscle forces, we take the kinematics, and then we feed it in the model. We optimize it for the energy cost function, and then we can determine some of the individual muscles. So we do these aims for the upper extremity work, and we examine young, elderly, and subacromial pain. So we are working on this portion right now, and the patients are coming later. Here you can see some preliminary data that I just compiled two nights ago on the plane coming. Here is the amplitude in millivolts, and the subject holds the arm, so like this. And then the arm is actually like this. And then the arm is supported with, because we don't have the arm support system yet, on the book, a stack of books. That's it. And I stimulate the brain on the right side, and then we record from the shoulder muscles. And what's interesting in this, as you can imagine, this is not done every day. This is a very difficult project also. And so what we did was that we targeted one muscle, and that target muscle was the, help me, this one, ECR, so the extensor carpi radialis. But we recorded from 4 muscles. Well, it's missing here, but this is the FDI, this is the biceps brachii, this is the anterior deltoid. So this is in 6 subjects, and you can see when the arm is supported, as you would expect, the motor cortical excitability coming from the brain is less. And when the subject holds the arm actively, then the magnetic brain stimulation causes bigger responses, as you can see it in the curve. So this is amplitude, and this is the stimulation intensity on the magnetic brain stimulator. And you can see that there is some muscle specificity. We were very happy to see that we can actually record very good data curve, because this data in the arm and the shoulder is not known. So this is almost totally new, even to us. First, certainly to me, I have not recorded it. Finally, the last few slides I show is by this very talented woman whose name is Claudine Lamotte. And we are working on theme 3 developed for this presentation, changes in gait adaptability and flexibility over the lifespan and metabolic cost. The idea here about gait adaptability and flexibility is beyond the standard coefficient of variation of gait, the step-to-step variability. We are looking at time series, so the Lyapunov exponent and dynamical systems analysis outputs of variability. Okay, so it's a different kind of, we measure the flexibility and variability with the dynamical systems outcomes. And as you know, thank goodness our gait is dynamically stable and highly flexible. We can make adjustments. If there's something on the floor, we can step over. And this gait adapts to goals and current conditions, support surfaces, speed. And flexibility is occurring by adapting temporarily and reversibly changes in the task demands. So short transient perturbations, as we heard it this morning a little bit too, cause adaptations, and depending on the age-related pathologies, these adaptations can be minimal or none, or can be still healthily present. What we are after here is that how age affects the gait adaptability and flexibility over the lifespan. And we, as I introduced the idea, we look at the adaptive control, how the adaptive control unfolds over time. So just to put it very simply, we have people walk on a treadmill for, 6 minutes, and from the accelerometer data from the trunk and the kinematic data and the force data from the force platform, we can compute time series correlations of the variability. That's what this means, over time, unfolds over time. So Sterju in Nebraska, and there are some other people who use this technique, but actually there are not that many people who use this technique. And so the cost of transport, which is in milliliters per kg per meters, so how much oxygen does it take to carry 1 kg body mass over 1 meter? That is the cost of transport. And you can see in the control down here, and the traumatic here, and the vascular patients, the same, even at the same velocity, well, these patients, of course, can just walk very slowly. I mean, there is a tremendous cost, oxygen cost, of carrying 1 kg of body mass over 1 meter. So the idea is that we try to understand how healthy aging and non-healthy aging affects this energy cost variability relationship. Part of the energy cost can be explained by biomechanical factors, but we now know that these factors do not explain completely the increased energy cost in pathological or aging gait. So, for example, my previous work, which I'm not showing here, shows a very strong high correlation in muscle coactivation, between muscle coactivation and the certain gait functions, so that it seems that the neural command to the agonist and antagonist muscles are dramatically changing, even with healthy aging, so that the energy cost in healthy aging is 20% higher for us than for the 20 years old. So what is the cause of this? Why is this happening? Nobody knows. So it would be nice to know, but we don't know yet. We don't know it yet. So that's what we are after. So there is evidence that, as I explained with the coactivation, maybe there is impaired postural control and muscle coordination coactivation, also contributing to the factor of increased energy cost. So here what you can see is a small perturbation, The control is the black one, the white perturbation is this one, and the medium perturbations. So the energy cost of healthy subjects increases when challenging postural control. Perturbation plus small path is present. We try to understand why is this happening, how can we change it, how can we minimize it. So to gain insight into the effects of age on the adaptability of gait by studying biomechanical and coordinative features. This is what I started the presentation, and I'm finishing with this idea, is that the single aspect approach probably will not explain behavior anymore. We are trying to step over that. So we always have two things, biomechanical and coordinative factors we are examining. And we will determine the metabolic cost of age-related gait adaptations. That is, we will measure dynamical systems output, we measure the neural activation, we will measure the kinetics on a force plate embedded treadmill, and the energy cost as the major outcome as the independent, as the dependent variable. So I will not go through these methods, but you can see what I mentioned under walking on the treadmill. Lateral perturbations, split back perturbations, speed changes, narrowing the path are the perturbations that we are interested in. And we measure all those things I measure to explain why is the energy cost going up and how is it going up. These are the dynamical systems measures here, the variability and stability measures. There are many things we are not doing. So if somebody is interested in potentially in bone and bone function, bone metabolism, bone biomechanics, we don't have any expertise in that. And there are some other ones that we are, of course, not able to accommodate. So to finish, the aim is to synchronize research priorities between these two locations, identify high-quality candidates with proper training, motivation, interest to engage in this trajectory, and make joint discoveries of scientific and societal relevance and increase the health span of older individuals. I have one more slide, a couple of slides of some of my students. You can see I have a large group of students, 12 of them PhDs, not all of them showed. And I have a large range of international and local collaborators, and now I am hoping to expand this to this continent as well. You can see these American collaborators and all kinds of people in Germany, in Canada, and so this is really a fun part of it. This is not just showing it off, but it is really, would like to demonstrate it to you that speaking to each other is really very important and very beneficial, and it's fun. So at the end, the race is on for the students to come up with good ideas. So this guy is doing the race, but what is really amazing about this is the performance aspect. So 92 years old. He holds the world record in the 60-meter dash, a Polish person from Poland. And so, you know, this gives inspiration to all of us that this can be done. Maybe, maybe not. So thanks very much for your attention. And then if there are questions, or I'm not sure how we do this time, I turn it back over to you.
Thank you, Tibor, for a nice presentation. So it's open for questions, for comments, practical or theoretical possibilities. It's open.
Thank you for the nice presentation. One thing which puzzled me is, if I didn't see incorrectly, you have, in terms of gait velocity, you have a minimum of energy for a certain speed, and so I'm not from biomechanics, so I don't know if that has an easy explanation or not.
Yes. So
yes.
right. So there are many studies that show this characteristic curve in healthy older adults. That when you walk on a treadmill and you walk faster than the preferred speed, when you walk faster than the preferred speed, or slower than the preferred speed, the energy cost of transport goes up. And that's what you see. So this is around the preferred speed, this triangle, they put it there. It's about 1.25 or something like that, I don't know exactly, meters per second. And then they started to decrease the treadmill speed and then increase the treadmill speed. Normally this curve is actually a little bit even bigger like this. So when you superimpose the young data on this, the energy cost of the young people is down here, 21% across about 20 studies. So there is a huge difference, but the shape of the curve is kept. So even in young people, when they walk on the treadmill at the preferred speed, is where the metabolic cost is the lowest. And when you deviate from there, you have the curve. There are... standing? Yeah. Well, standing would be 1 met. That would be what, 3 point? Well, this is complicated. Well, you couldn't conclude because you would multiply by 0. So it would be difficult because there is no. So this to express it in terms of metabolic cost. So then you would have to go to oxygen uptake, like sitting and standing and walking. So 1 met is when you're sitting is 1 met. When you're lying is 3.5. Is that what it is? 3.5 milliliters per kg, roughly. Yeah. So very low, very low. I would have to know the body mass for these people to get it in. Yeah. So many of us would like to know why there is this 20% difference, and that's what's driving the project, because it's not good for us to walk down on the Paulista and having 20% more oxygen uptake needed to walk at the same speed as anybody else. Maybe mitochondrial function, maybe mitochondrial dysfunction. We showed, and Peterson and other biomechanics people showed now that there is really a very strong linear correlation with the muscle coactivation. What that means is that for some reason in the inhibitory system, there is an aberration to inhibit the antagonist muscle. So what actually happens is there is a larger muscle mass involved in the gait than necessary, which increases the cost. But that flexor muscle is not doing work. It is just an isometric mechanical work. So while we showed around a 0.72 correlation with the level of coactivation, the magnitude of coactivation between pairs of muscles and the metabolic cost, others are trying all kinds of mechanical measures that stiffness, the work, but those don't seem to pan out. It seems to be a coordination cause. Yeah, or you have the mic.
More questions?
Is nice presentation. Congratulations. Is the APA study being held in your laboratory or in the collaborator laboratory? Because I've already asked you about APA studies.
Yeah, so as we speak, we just submitted the ethics, whatever it's called here, the ethical approval or, ethics. So we just submitted like this week. So it's going on in our lab, and we are at the pilot phase, and we are doing the arm swing paradigm for now to keep it simple, and It is very complex to figure out exactly where to give the stimulation. It's very difficult. So if I don't bore you, I just explain it to you so you learn about the thinking process, is that you cannot just give it X millisecond after the tone. So that the tone comes, beep, so you swing your arm, and relative to this tone, you give the stimulation. Well, you know, you can swing your arm, beep, now, late. Well, we gave the stimulation, so we have no data because we have already given the stimulation, but I mean, it's like it's a wrong time. So to give the stimulation at the proper time, we spent about 3 months on it to figure out how to do it. Yeah. Well, we are, you know, we cannot do it with the supplementary motor area with TMS. We are doing the primary motor cortex, so that's a limitation. It can be done. TMS can be done in the supplementary motor area, but I don't think I can do it. So what we do now, so that I give you the answer after all this work, is that we have the people, the subjects, swing their arm 20 times, and we analyze the data. We look at their average reaction time, and we look at the electromechanical delay between the muscle response, and we take that as a target, and then we time the stimulation as if all of the trials came about at that time. So we have about a 60% yield now, meaning that we do 100 trials, we have data, useful data for 60 trials. But we have to optimize this because for old people, we cannot swing the arm 200 million times. So it's very, very challenging. So 5 people working on this project right now. So, yeah.
Other questions?
You can ask it in Portuguese and then somebody can translate it.
Yeah, sure. Could be made in Portuguese.
I know the language is a big issue.
Is there any physiological technique we could use with perturbed posture, like those we talked about today?
Physiological measure?
In terms of understanding what happens in the brain to respond to unexpected perturbation.
Mm-hmm. Well, so there are several studies that published the stretch reflex response. You need a lot of trials, and then you average the responses. So if there is a, well, yeah, maybe. So let's assume that you have the perturbation here, you have the perturbation there, and then you have the EMG of I don't know, the gastrocnemius and the soleus or biceps femoris, and this perturbation has to be pretty fast. And then after the perturbation, there is a short latency, M1, M2, and M3 response. Muscle response 1, muscle response 2, muscle response 3. This tends to be around, maybe around 30 milliseconds. This is around 50, 60 milliseconds, and this is over 100 milliseconds. So if you have enough of this, then maybe you have the 3 waves. Maybe. But you need maybe 30, 40 trials per condition to get stretch, the perturbation, the stretch evoked response in the muscle. So that would be one added physiological beyond the latency, for example. You have to see, so you would have to filter the data and then rectify it, and then see whether your perturbation is fast enough to evoke a stretch. Okay, clear? So this is a stretch response. So if you have a shortening muscle response somehow, I don't know, like this, then there would not be a reflex because you have to stretch the muscles for the muscle spindles to come in. Well, yes, of course, you can do peripheral nerve stimulation paired with it to have a reflex evoked, an H reflex evoked. Well, in the head it would be a little bit more difficult, but like a 40, what is the speed, 40 centimeters per... I don't think we are going to do TMS there, no. So that would be very difficult. But I think peripheral nerve stimulation and the stretch reflex could work. I can't think of anything else right now. Maybe someone else can.
Thank you, Tibor. So let's move to next presentation. At the end, we can return and make an overall discussion. So we are moving to Andrea's presentation.
Do you want to use this? Yeah. And then you can use this remote. And then this one goes in there. It will take just a second. And then we figured it out last time. Yeah, that's okay. We know this message. And then this one, right? Press any one key immediately right of the shift key on the left. This one? That's okay. It did the same thing to me.
You press the key
I
to
did.
the right of the shift key.
Yeah, I did.
Yes. On the left
Identifying
side.
your keyboard. Just we have to wait a little bit. It did it for me, but we had to go through all these error messages. We just stepped through the error messages.
And my computer is lazy.
Oh yeah, maybe this is a little bit smaller. So I don't know what it is doing.
Shift the slides.
Yeah, maybe it's easier.
Muda pra mim então. Will help me.
And here is this one.
Okay,
and
thank you.
Stand there, and then you advance it for him. Yes. For her, excuse me. And
Eu tenho que ficar lá do outro lado, né?
Hello, good afternoon, everyone. So I'm really happy to be here. Thank you for coming. So I'm a physical therapist, and now I'm a postdoctoral researcher at the Institute of Radiology, University of São Paulo here. And currently I'm studying postural control, anticipatory postural adjustments in Parkinson's disease with fMRI. Okay? And today I'm going to present the work Dr. Tibor and I developed to be run in his lab in Groningen, called the Neurocorrelates of Balanced Training on Inhibitory Cortical Circuits in the Elderly, comparison between conventional and new approaches. I'm going to go through the context of our scientific problem, then how we think we could answer some questions, okay? So as we know, life expectancy is rising worldwide, which means that there is an increasing number of elderly people in activities that challenge their posture control. For example, dimly lit areas, irregular surfaces, and dual tasks. So these situations can lead to fall. And falls related to poor posture control are the leading cause of injuries related death and hospitalization, with over 1/3 of elderly population over 65 years old experiencing fall at least one time each year. Okay, so it is a very important issue to be investigated. And let's start explaining why, as we age, postural control decline. This is because we suffer structural and functional reorganization of our neuromuscular system. For example, reinnervation, axonal reinnervation, coactivation of agonist and antagonist muscles, problems in spinal and cortical circuits, and shrinkage of many cortical areas related to postural control. And there is evidence that the motor inhibition is decreased in the elderly population. So this motor inhibition is largely regulated by the gamma-aminobutyric acid, GABA neurotransmitter. And this evidence suggests that the decrease in motor inhibition seems to be related to longer reaction time, impaired coordination, and decline in postural control. But fortunately, at the other side, many studies, as we know, have shown that exercise induces neuroplastic changes in the elderly, even in the inhibitory circuits of the brain and of our spinal cord. So I will go through briefly in some studies that assess the inhibitory control of elderly people and the effects of exercise. So they found that after 2 days, only 2 days, or after 13 weeks, it is possible to regulate the inhibitory system of spinal circuits after balanced training. Okay, but they found in spinal circuits, but findings about supraspinal circuits are not well understood yet. So they are inconclusive. So in the elderly, one study compared one intervention based on balance and strengthening program, okay? But one group did mainly balance practice, and the other group did mainly strengthening practice for 6 weeks. They found that both groups improved the posture control and they reduced cortical spinal excitability, but they didn't see difference in the inhibitory circuits according to the kind of interventions, different of what was found in studies with young people. So they modulate their inhibitory system according to the kind of intervention they are submitted. For example, when they are submitted to strengthening, they enhance the cortical spinal activation. While they are submitted to balance intervention, they increase the inhibitory transcortical effects. But as you see, they are really recent works. So we don't know yet about what happens with supracortical spinal circuits after different interventions in the elderly. So this non-specific adaptation of the elderly based on each kind of intervention raises one question. Yes, this is because in this study they didn't distinct enough the kinds of intervention, or if the elderly, the aging affects the old adults' ability to to benefit from unique stimuli to target specific postural dysfunctions. So we don't know yet what happened. So our objectives are threefold. The first one is to address the plasticity of inhibitory circuits to two balanced trainings in the elderly. Second, to address the specificity of each balanced training on the inhibitory circuits, and to correlate inhibitory circuits changes to postural behavior after each balanced training protocol. Okay? So we are going to recruit 48 participants that will be assigned to 3 different groups. One group will be the conventional balanced training. I will explain better. The other, perturbation-based balanced training. And the last one, educational group. So we have the CBT, PBT, and CO groups. All the groups are going to start with a warm-up, start and finish with warm-up exercises. Then each of them will do the specific intervention for 3 times a week for 8 weeks. So the CBT training will perform exercise based on the guideline of Otago exercise program. So there are conventional exercises that in a clinical physical therapy they will perform. So this exercise was developed to decrease the fall incidence in the elderly. So we have exercise for the knee, all the muscles of the lower limbs, and to increase balance using static exercises to improve anticipatory balance. It's not reactive here, okay? Here is how they are going to do this kind of exercises. So we are going to focus on 6 leg muscle strengthening with up to 4 levels of difficulty, okay? And 6 balance exercise with up to 4 levels of difficulty. So they are going to start with ankle cuff that they could perform 8 to 10 repetitions, okay? And they will progress, and we are going to progress the weight of the ankle through the weeks, okay? And we are going to progress this exercise from eyes open with support to eyes closed without support. The PBT training will suffer 40 discrete perturbations of the body using the caring system, computer-assisted rehabilitation environment that is available in the lab, in the Dr. Tibor's lab. It's a really nice system. It's a virtual system, and there is a there are force platforms, and the surface is able to displace in many directions. And they will underwent unpredictable perturbations at 4 directions with a translation of 9 centimeters and 35 centimeters per second in velocity. And we are also going to progress this program, this intervention from eyes open to eyes closed in the last weeks. And the control group, they will have to attend meetings, 3 sessions per week. These meetings will be the same time of the other interventions, 40 minutes, for 8 weeks. There we are going to talk about polypharmacy, memory loss, sleep disturbances, and falls. We are going to use 2 force plates of the Kohn system, electromyography of the tibialis anterior, and kinematics of the right malleolus and trochanter major. And for TMS, as you saw with Dr. Tibor, we are using a double Kohn coil connected to a MAG stem 2002 and B stem 2 on the left primary motor area, M1. And we move the coil in steps of 0.5 centimeters over the M1, contralateral to the tibialis anterior that we are assessing, to get the motor evoked potentials. And we are going to use paired pulse TMS with an interstimulus interval of 2.5 milliseconds to get this variable, CC, is short interval intracortical inhibition to assess the inhibitory circuits, and an interstimulus interval of 13 milliseconds to assess the intracortical facilitation. Okay? So we are going to perform 10 tests to get the motor evoked potential, 10 to get CC, and 10 to get ICF trials. So here is the design. So how we are going to assess these people. So firstly, they will do the pre-test with 10 trials, but these trials will be performed in 4 sensory conditions that Dr. Tibor showed. Eyes open, eyes closed, on a foam surface or a firm surface, okay? And this will be combined. After each subject, we are going to perform this specific intervention. After a post-test, after one hour after the last section, the first post-test, and then retention 72 hours after the last section. So it was the same paradigm as the pre-test. So here is our chronogram. So as you see, we intend to finish this project in one year. And I hope to get the grant from the Science Without Borders. So the deadline to get the result from there is the next week. So let's see. I'm crossing my fingers. So the main reference, I can send the slides for anyone who wants. Okay, thank you very much. Some questions?
It's open to questions.
Em português? Pode ser em português, ele falou.
As you wish. Ok. Parabéns pela apresentação. Eu gostaria de saber o raciocínio clínico por trás da configuração dos 3 grupos e a hipótese que vocês estão estabelecendo em relação ao grupo PB... Da perturbação? Por causa da complexidade, por causa do ambiente virtual, por causa da somatória das duas coisas? O que vocês estão imaginando em termos de hipótese e de construção do raciocínio clínico em cima da construção dos 3 grupos?
She asked why we decided to have the conventional group and the perturbation group. Why is the neurophysiological base for this? Okay, why our hypothesis?
In terms of the environment, I mean, is the virtual environment the main point, or is it in terms of test complexity or difficulty? What are you wondering about this in terms of hypothesis?
This is because there are some evidence points to better results when the person is performing a perturbation training. This is because the reactive control of the muscles are more prepared for all of the requirements of the environment. So we think that in this condition they will have
more inhibition of the circuit. Okay, we'll have an increase in the motor inhibition because of this preparation that they have to be this state of alert. Okay, and in the other case, the conventional group, they don't train posture at all, because they are training strength, they are training even in different sensory conditions, they are training other aspects of most motor control that could be not related to the inhibition circuits. I don't know. What do you think?
This is the testing paradigm, right? This is the testing term paradigm. So some of the problems are then with the testing, you know, the effects of the testing, the effects of the interventions, is that the control of the test is pretty poor. So Berg balance test, you know, those kind of things. I mean, they are nice and helpful and all that, but so we try to quantify and really control the responses the subject give to a stimulus. And we hope that there will be a transfer of specificity from the training, from the specific training to this environment versus the active control group is the strength training.
The last study I showed, the only one that compared the different interventions in the elderly and saw the inhibitory circuits, they saw that they decreased excitability and they improved posture. But they did a strengthening training with that kind of balance training, okay? Just to prepare like a stable balance training, I would say. But they didn't see the difference between these kind of interventions. We think this is because they didn't perform a distinct kind of intervention that that challenged their posture, okay? So they can benefit from any kind of exercise, but we think that the kind of intervention that perturbs their posture, that challenge their posture, could be more could be regulate even more their inhibitory circuit, because there are studies that show that that they have problems in reactive responses, and these problems, reactive responses, are related to problems in the neuromuscular systems. Okay.
And something for the future, not for now, because if you intend to finish your project in 1 year, you have enough group, 3 groups are enough. But maybe it would be good to think in another group in which we can challenge the anticipatory postural adjustments in the conventional environment, because maybe someone can argue that maybe the environment is the most challenge point, and is not what you are wondering. You have another hypothesis. That was the reason of my question. So it's good to think, is it possible to plan a group in which they are enough challenge in the real environment, like the conventional treatment or program we usually do, but not in a way that we would like to improve reaction, but we would like to improve anticipatory adjustment. So it would be nice if we have this other point of view and to compare the 4 groups. Just to think about.
Yes, thank you.
This is just curious about these TNS and how long does stimulated?
I think Dr. Tibor can answer this.
What do you mean? How long does it? What part? The preparation or the stimulus itself?
The stimulus itself.
Oh,
I
it's
saw
in,
that.
well.
You
So
have
the magnetic field is given up in a microsecond duration.
Okay, but
microsecond
yes,
duration.
I saw, but just one shot.
Oh no. We do multiple trials. So we go every 5 seconds. We do I don't know, 20, 30 trials.
Okay.
And then we average the responses.
During the whole protocol?
Yeah. So the way it goes is as follows. The person stands on the foam, eyes closed. We put the coil on. We have preparatory measurements. Okay. We have electrodes on the leg. And every 5 seconds, we give a pause. And the person is watching a cross on the wall or whatever we do.
Okay.
Every 5 seconds. So we do 12 responses, 5 times 12, so that's the time.
Okay.
Yeah.
Thank you.
Yeah. So that's why I showed the slide. I thought maybe there would be some people interested in seeing.
And one thing that I forgot to say is that in that study with young people, they found this difference between the interventions only in the more challenging conditions. Okay, only in the phone condition.
So, as you can imagine, this issue of specificity is it's in every textbook, right? So, I take my sword out and I stab the specificity. So, Andrea just showed the Spencer paper, which I reviewed. There were non-specific responses, okay? I think the measurements are poor. It cannot, either the stimuli are poor, not distinct enough, the measurement are poor, or both. I give you an example. So we just reviewed a huge body of literature on gait speed. Very important to move fast, right? Old adults. So we reviewed 42 studies in 3 different kinds of interventions: strength training, coordination training, multimodal training. Guess what was the difference in the improvement in gait speed, the increase in gait speed between 1, 2, and 3. These are supposed to be gold standard. You read the introduction of the multimodal training. The multimodal training is superior to anything. I mean, this is it, multimodal. So what do you think were the changes with strength training in the gait speed? Meta-analysis, for many studies, averaged. And then after coordination and after multimodal, what do you think? How much was the improvement? Just guess. How much faster did these healthy old adults walk after the intervention? What do you think? Absolutely correct. 11%. Right on the money. So I tell you, the fast gait speed, totally independent of the 3 interventions, improved, guess what? 1.2 meters per second. Improved, 1.12 meters per second, 0.12 meters per second after strength, 0.12 meters per second after coordination, and 0.12 meters per second after multimodal. My sword just went into the specificity. There was absolutely no evidence for specificity. Anything these old adults were doing was working. So just have them do something, they will improve. That's where we are right now, because of the tools are so poor.
Nowadays, we have lots of researchers and physical therapists arguing that we have to train test specific, and training should be test, should be specific with regards to the test. And we see that even if we don't have a test specific training, we have the same improvement. So maybe we have improve our ways of measure, or we have to think about a different way.
Yes, that are our guess. Or they didn't use distinct enough interventions across group, or stimulus, or the aging leads to this problem of have the specificity according to the kind of intervention. So we need to assess this in more details and to have more robust interpretation about this. But it's a real problem in our day by day, our routine. Yeah. So everybody says, oh, the PBT is better than the conventional, but we don't know why this is better. So maybe it's because these inhibitory circuits that are related to poor posture. Maybe it's because this. Yeah.
Here we have a question from Luis Mochizuki. He's watching us through internet. Hi, Andrea and the fellows. After two very nice presentations, I want to address one question to Andrea. Why do we expect changes in anticipatory control of if both your physical exercise and virtual reality deal with compensatory responses? Best regards.
So I didn't understand, sorry.
I repeat.
Okay, thank you.
I want to address one question, Andrea. Why do you expect change in anticipatory control if both your physical exercise and virtual reality deal with compensatory responses?
So
I would.
We are not doing the virtual reality. So this is important because I would like you to see this caring system. But we are going to use this carry system to do this discrete perturbations. We are not using the virtual system, okay? Maybe after we try to use this virtual system, but we are using this because they have the moving platform, okay? So there is a complete system to assess postural control. This system we are going to use to perturb the participants, okay? And we are not assessing the anticipatory posture adjustments, okay? We are going to assess the elderly people in the 4 sensory conditions, okay? So with TMS and the center of pressure, but it is not only the anticipatory posture. We don't have a specific paradigm to assess the anticipatory posture adjustments. Okay.
So the evaluation will be purely reactive.
The evaluation, yes.
Is reactive.
Reactive.
I think this is the point of Mochizuki's question. I was thinking just about this because your traditional training is based on voluntary movements, like in raising the leg or making any kind of movement. So it is typically anticipatory, not compensatory. And the second one, the perturbation is reactive. So the participants could not anticipate the perturbations.
Yes.
So I think it's an important point between these two
kinds of training.
Yes, two training. And returning to the question of specificity, we are going to evaluate in reactive conditions. Would not be a good idea to have both, to have a test using evaluating anticipatory control and the other one evaluating reactive control?
I agree.
Yeah.
If we can do it, if we can squeeze in all these tests, it would be a good idea.
We could include the step initiation to see the APAs. Would be a good idea to assess, yeah.
I think maybe using oscillatory movements. So the person can anticipate if kept in a same rhythm. The participant could, using the same device, you can evaluate both. If you use oscillatory movements, in the other condition, unanticipated reactions to platform movement, could be a good improvement.
And I don't know if it is possible to assess TMS metrics during a step initiation or no. That's why it's eyes open, eyes closed. This is because it's already settled. Yeah. This. Yeah, we could see all, but not with the brain stimulation together. We are going to do the TMS with as I put there in the design. We are going to assess the TMS during these 4 sensory conditions. And we can at the same time see the center of pressure, but not a step initiation, as he said. We could do this separately.
That's great. We have now, I think, if you have no more questions, we could have a break before presentation of Professor André Kohn. Set up the presentation. People who want to go to washroom for a very short break before we continue. Okay?
Thank you.
Okay, good afternoon. It's a pleasure to be here. I didn't prepare something really didactic as Professor Tibor prepared. If you could help me. I just prepared something with the view of showing him some of the stuff that we are doing, which could perhaps in the future lead to some collaboration. So I apologize for the audience for the lack of, it's not nice, it's very direct to the point. I just selected a few of our research. One research which is not here is standing on foam and different surfaces with light touch or without light touch and studying muscle synergies. So it's a very lots of data. So it's kinematics and dynamics and EMGs of lots of muscles, and we are studying the different synergies that could occur when you are in more unstable situations. But so I'm not reporting this. Okay. So this is a recent work of ours in which we studied something very simple in the spinal cord, which is our main focus, which is differences in presynaptic inhibition in spinal networks. Next one, please. The subject is sitting and having a feedback either of the torque of an isometric pedal or a free pedal, and then he has the feedback of the position of the pedal. So it's a force task and a position task. We only did young subjects, and I think older subjects and persons or subjects with different pathologies could be tested with this sort of scheme, and we only tested something very simple in the spinal cord. So going upwards would be very interesting, and I point that out as possible next steps. Okay, so just synthesizing, we have in the spinal cord some neural circuits which you shown there in a not very nice picture, which I tried to draw, which are the presynaptic inhibition. This loop, neural loop in the spinal cord is able to adjust the gain of feedback coming from the muscle spindles. The spindles are very important to give feedback on muscle length. So probably, so I would expect that in a position task where the pedal is free, you would expect more importance given to the feedback from the muscle spindle. So that was our prior hypothesis. And when the pedal is fixed in an isometric position, I would expect less importance for the feedback from the muscle spindles. But that's just a guessing. So there are ways of checking how this presynaptic inhibition circuit works in the spinal cord non-invasively, and that's what we've done. So just in a nutshell, what we found is in a force task, the amount of presynaptic inhibition was much larger than in a position task, which can be shown. I don't have a laser pointer. So, but anyhow, what you can see on the right, you do? Okay, thanks. I'm sorry I didn't bring one. The middle? Okay. Okay, great. Thanks. So what you see here is the amount of presynaptic inhibition in the subjects that we tested was somewhat or pretty much lower than in a force task, and this gave support for our previous hypothesis that when you have a pedal which is free, you need more feedback from the muscle spindles, and so the gain of the feedback should be larger. So I just can envision that this could be very interesting for testing older subjects, testing different neurologic pathologists, and how different pathologists have these presynaptic inhibitory circuit affected. So it's not a very difficult test to do. Other things, what we, in terms of next steps, so that's one reason why maybe we are trying to show Professor Tibor what we do. It's, for example, going upwards and trying to understand what happens in more upwards levels. So we are in a very segmental level. So sub-TMS, double TMS stimuli, cervicomedullary stimuli, so very interesting stuff can be done and in a very simple, so training, so different kinds of training and how this training can modulate these sort of spinal cord circuits. And also, so we have one ongoing project in which we are doing cortical muscular coherence, so EEG plus EMG, and also we are doing fine wire decomposition of EMG in spy trains. So that's a better way than using pure EMG. So if you want to interrupt, okay, in terms of any question. So I'm trying to show some points of contact and some possible extensions. And also we could perhaps think of standing instead of sitting task and trying to measure similar things. Okay, next one. So this is one of the only works we have done with brain signals. Next slide, please. So in this situation, there was a servo motor which, and the subject couldn't see his foot, and this servo motor, when the computer started to gave an output signal, then the angle changed from 0 or let's say the angle from 90 degrees, and it changed to 90 minus 11, and then came back to 90. So it was really, let's say, a fast dorsiflexion. And there were two conditions. One, the subject didn't do anything. In the other case, the subject pressed a button here whenever he felt the foot moving. So that's not obvious. So this is not too fast. Okay. So older people are expected to have a lower sensitivity to proprioception. So what we are checking here is proprioceptive signals from muscle spindles and how they reach the brain. So that was the whole thing, and this was done by Diana Toledo, which took her PhD with me. So we have no voluntary response situation, the voluntary response situation where you had to press the button. She measured reaction time, cerebral evoked potential, and beta band EEG, desynchronization and synchronization of cerebral activity. So basically the results of evoked potentials. Bad news again for the old people. So the responses are smaller and come later, are slower. It's not so visible here, but they are smaller. It's quite visible. So the young subjects gave a much higher influx from the pedal movement. Again, for the response case, the button pressing the same thing. Okay, next one. I'm just going to point out one thing. So the amplitude for the young adults is much higher, significantly higher than for the older. So the influx is smaller, unfortunately for me, because of my advanced youth. And the latency is larger. The laser is, I don't think it's working. And the reaction time is also larger. Okay, next one. And this is ERD and ERS. So this measures the power of the electrical activity of the brain. So, and the interpretation is not so easy. So basically when there is an ERD, the desynchronization, the interpretation is that it's working? Oh, maybe it gives some, okay. So when this goes lower, it means the brain is more active. It's working harder, okay? And so the interpretation here when the subject had to press the button was that the ERD, that then the older people had to pay more attention and process more the data because of the lower influx of sensory information from the muscles and the longer latency, and probably also there is a more dispersion. So when everything gets slower, it's more dispersed. There's something which it's more difficult to explain is the higher ERS for the younger subjects. I point out that this could be very interesting to use, for example, a sub-TMS analysis or double TMS analysis, for example, to study such a response, okay? This work is just a modeling work, but to study quiet standing with large-scale neuromuscular models. So we are modeling lots of neurons in the spinal cord, muscles, the whole biomechanics. We are simplistically supposing an inverted pendulum for quiet standing, which is pretty good for unperturbed standing. I'm going to read just the conclusions, what we think from this. So the interaction of spinal neural circuits with proprioceptive feedback and biomechanics, together with constant intensity, but of course random, brain descending drive is sufficient to reproduce experimental data on human quiet standing. So the simulation results point to this. So there is no need to postulate brain-generated pulses, commands like Lorem and company do. No need to postulate open loop versus closed loop like Collins and DeLuca postulate. And no need to postulate cortical long latency feedback. So as I point out, I'm not saying they don't occur. They are not necessary. They may occur in different levels, in different conditions. But in principle, the spinal cord plus tonus drive, let's say this way, is sufficient to reproduce all or most of the data that we find in human experiments. Okay, So just to take an idea, I won't explain anything, just to see numbers. We haven't modeled the vestibular, neither the visual, because of lack of time, so it requires lots of effort. So we are, maybe give one more. So we are modeling the somatosensory system around the leg. We have several thousand motor neurons, interneurons, more than 1 million synapses working in the spinal cord, plus the sending drive, which is the stochastic point processes. We are modeling muscle spindles, muscle dynamics, joint dynamics, and this was done by Leonardo Elias and Renato Watanabe from my lab. They are engineers, and this is a big work in terms of modeling. Okay. Another thing which we are involved is in stochastic resonance in sensory motor control. I provided an example which a student of mine, a master student of mine, just done in simulation, but I'll show real data. So this is a single neuron simulated. This is a sinusoidal input, except for the beginning, because the neuron was just sleeping and then suddenly it received a kick. So it fired, but then in the other cycles you see it hasn't fired at all. So if you sum a little bit of noise on the input signal, you have the reliable firing of the neuron. This is like just a simple example of a stochastic resonance for a single neuron. This happens in human beings. Let's take a look. What we did was the following. We stimulated with random signal, not pulses, random signal, either at the back of the leg or the front, tibialis anterior or triceps surae, with stochastic stimuli, okay, or both. There is a group, Lorem's group, which has provided a very interesting hypothesis that the tibialis anterior, because it's silent during posture, it would be ideal to signal the angle of your postural variations. So we expected as a prior hypothesis that stimulating the tibialis anterior would be give the best results. That was our working hypothesis. Okay, just going to the results. This is a single subject. This shows both the center of pressure and the center of mass. For TS stimulation, back of the leg, TA stimulation, front of the leg, both together, no big difference visually. So control, you see, it's much more spread out. Okay, this is work by Fernando Magalhães and myself. And looking at the overall data, no basically significant difference between control and simulated cases. So we have an improvement, a decrease in postural sway with the addition of stochastic stimulation. So this is improvement. So this could be good for patients. Okay. But there's no difference between tibialis anterior or triceps surae, or even when you sum both. Okay, possible next steps: going to different levels and see where you can find effects of these random stochastic stimuli on different parts of the nervous system. Okay, next one. This is a more theoretical stuff, but as I find it very interesting, I will present it. There were some groups. This is by a paper by Farina from Göttingen. Some groups have proposed that what reaches the motor neurons, a common drive, let's say from the upper centers, this common drive is mapped linearly to the muscle force. Okay, so basically the muscle force is a filtered version of what's commonly coming down from the brain. Okay, so what would a beta oscillation, which is supposed to come down, have? How could it affect the force output if there is a linearity hypothesis? So if If what comes from the brain is copied to the force, that means that 20 hertz, and this is data from Orizio and company, this is the frequency response from the tibialis anterior muscle. This is frequency, and you see 10 hertz. 10 hertz compared to 1 hertz is already very attenuated. 20 hertz would be down here. So nothing would reach the muscle, the force. Okay, so if these oscillations that could be coming down from the brain can affect the force, it couldn't be by the linear manner that some people have proposed. So a doctoral student of mine, he did some very mathematical stuff, which only he understands, I don't. I just said, oh, try to do this. And what he found is a 20 hertz descending command to the motor neuron pool was mapped to a force output at 0 hertz. Very interesting. Okay, so then we already had the simulator set on. He just changed a little bit the descending command. So all the motor neurons are modeled by ionic channels. Okay, so it comes from ions to behavior. Okay, then the muscles are modeled and so on up to force. And the descending commands are spike trains coming from the pyramidal tract. Okay, next one. So this just came out, Journal of Neuroscience, which is reasonable. Next one. So input coming from pyramidal tract. 3 cases. One, it's a Poisson process, so it's random, but the mean rate is 65 per second in blue. Then we oscillated the mean rate at 20 hertz. Okay, so the mean rate continued to be the same, and here we decreased the mean rate to 58 per second and kept the 20 hertz. Okay, let's see what happens with the force. Without the oscillation, it gave just this mean level of force. When you added the 20 hertz, the force increased and was kept. Okay, so this is very different from what other people have shown. And when we decreased the mean rate to 58 but kept the sinusoid, then we were able to keep the same force level. No, I think the battery is almost gone. So if you compare the green with the blue one, you see the level is more or less the same. And what did you gain? You have less energy expenditure by the nervous system, because it's firing at a lower rate, as we saw before. That's at 58. Okay? The explanation for this phenomenon without the mathematics is that this is a raster plot here below, okay? And the motor neurons are numbered from 0 to whatever, and on the brown one you see this ellipse. You show more recruitment of new motor units, and they are the stronger motor units. So that's why you have an increase in force just because of a 20 hertz oscillation, which is coming down. Okay, so this is pretty new stuff. Okay, next one. And then I said, well, what happens if you modulate slowly the amplitude of the 20 hertz, just like this? Okay, on the right here, down here. This is called an AM signal. Okay. And what you find is the following: if you modulate this by 1 hertz, the force will be modulated by 1 hertz. If this happens in the real nervous system, nobody knows. So this is a strong hypothesis, and experiments should validate these simulation results. These are not easy experiments to be done. Okay. Okay, thank you very much. So I hope we can find some tangency points and we can collaborate in some future. We have one work in which we studied plasticity in the spinal cord circuits in response to power training and force training, but the lady went there to have kids and so on, so we didn't write the papers yet. But there is some plasticity in response to And this we did together with Valmor Tricoli and Ugrinovic from this department here. Okay, so we have some other stuffs, and okay, thank you very much.
Let's open to questions. To Dr. Kohn. I have a question. What do you think about what changes would you expect to find in if a person is engaged in mental task like some calculations and the results in your model?
Yes, I agree entirely. So when I said quiet standing is really the guy doesn't have a double task. It's not challenged, and so just spinal cord could be working. So anytime you ask for something else, then I agree entirely. Cortical inputs besides the descending stochastic thing has to go in, and so this is for so no attention required. So you're standing and maybe looking at nice girl, okay, and then that's it. So maybe the spinal cord is enough. So I'm saying sufficient. So our paper cannot say, oh, that's the way it is. So we say it's sufficient. So we showed, it's by Gatev and Mark Hallett. They have a very nice journal physiology paper in which they analyze the cross-correlation between solus EMG and the central pressure. And they get something like 300 milliseconds. And then we went to our model, there it was. And there was no delay near this value any place in the model. We had delays of 15 milliseconds for nerves. That's it. So apparently in a macro scale, the model is pretty good. So, but I agree entirely. Any more complicated stuff you do, we would be very interested in doing experiments like you do with perturbations. Then we would have to at least put the hip, so more muscles, okay? So in a double task where you have more attention requirements and so on, then something gets more noisier. But very good question. I don't know the answer. So what I said was just in a very relaxed, quiet standing, no attention case. And so I think probably that's not very incorrect.
And what do you think is the role of the cortex to maintain quiet posture?
In these very special situations, it's giving firing for muscles. It's not constant firing. It's, as I said, a stochastic process with a mean which is constant or maybe sinusoidally modulated. And all the rest of, let's say you're beginning to fall, all the rest, the spinal cord is entirely sufficient for giving all the corrections based on feedback from muscle spindles, Golgi tendon organs. We have reciprocal inhibition networks working in our model. So it's the whole spinal cord. And the brain is giving this stochastic drive. One difficulty we had was that the muscle spindles have gamma static, gamma dynamic control. And so in every situation we had to set these values within a given range. So of course in a human being these are being modulated a long time.
I have another question. We're talking about...
I hope we can collaborate more. I think we have more points of tangency.
I hope so.
We only have one paper together, but I think we could have more.
It's time to increase collaboration.
Oh, by the way, we have worked a little bit with those stuffs. Okay?
Okay. And in the morning we were discussing about latence, different latence, depending on the load. And similar, same model we used with load release. And when we compared 5 against 10% of body weight, we found very large differences in latence for gastrocnemius responses.
For perturbation?
For perturbation,
okay.
yeah.
Okay.
As expected, the magnitude of the muscular reactions were different regarding the load, but the surprising results were different latencies. And for the higher load, the participants responded faster. So the latency was shorter for the 10% compared to 5%.
Mm-hmm.
So could you enter into this discussion in terms of providing some insights in how could we interpret this effect?
So just the last sentence, if
so
you could.
How could we are discussing about possibilities as a person receives a higher perturbation. One possibility could be, for example, increased sensory stimulation from different sources, from the muscle spindles, for example, with a faster stimulation. Could you think it would be a good explanation for different latence?
Could be. I think, as I said, I'm sad that I don't have more students, because we would be very glad to model vestibular system adequately. I have somebody who promised, but it's an undergrad, to do a model of the foot soles, which also I think have some feedback. So I think in these perturbed cases we would have more the need of more feedback, so we can have a more realistic picture. So just with the spindles, I'm not sure how much we could go further, but it would be a nice thing to model, definitely. But maybe your suggestion is maybe you have more discharges, everything is more recruited, nearer to the recruitment. But good question.
Okay. Thank you. And
well, thank you very much for the nice talk. Of course, I'm familiar with particularly the last paper, the Journal of Neuroscience paper. I saw that recently just came out, so it's quite interesting. So, in quiet standing, in young and old individuals who are supposedly healthy old adults, we find quite big differences in the inhibitory control. So we can measure, right, with the TMS, we use this double pulse and this and that, and so we find that there is a behaviorally meaningful correlation, so that the old adults use so there is less inhibition to maintain standing balance by watching across. That's the task. And we can manipulate it further with the foam and this and that. But the bottom line is that even at the quiet standing balance, not to mention the further more complicated tasks, there seems to be a strong effect of the inhibitory control, meaning that there is less and less inhibition. They need to excite the brain more to do the task.
So probably EMGs are more pronounced or in more
yeah, we
higher
are careful.
amplitude.
We are careful with this because we try to match the background EMG upon which we evoke the responses.
So the older people do not have higher EMGs than they do. So that's one point. I don't know, but it's also a very interesting thing to try to model.
So the model that you showed relative to Farina, the 2015 paper by Farina, the linear versus nonlinear mapping. So what is the role of this beta oscillation? That was a little bit too fast for me.
Now the role that I could think of is because it's being suggested that it really appears whenever you are holding something, and maybe it gives like a baseline for a force, and then to be varied up and down from a baseline level. Also, like I showed on the right side, the nervous system could spend less energy in keeping a given force, either for gripping or lower limb. So if it employs this 20 hertz stuff, you have less spikes per minute, for example, which means less ATP. So, as I said, that's a hypothesis.
Where do you measure this beta oscillation? Like what?
We are business models. So we are applying these.
What do you assume if it's coming from?
Yes, there's no way the downcoming information is coming from spike trains. So what we impose like a stochastic point process, so random discharges, but the mean intensity. So instead of being constant, then it goes up and goes down. It's like an FM in one sense. Okay, so the mean rate goes from 65, let's go to 70 something, then goes down, and this 20 hertz oscillation around the 65 is the 20 hertz which I'm talking about.
So this oscillation is coming down in the pyramidal.
Yes.
So this is the summated effect that comes from all the circuits impinging on the.
Exactly. The big difficulty is when we wrote the discussion is the problem is everybody just measures EEG and beta and that's not what's coming down. That's a complicated resultant of millions or many thousands. So our thing is much simpler. So that's maybe why we can reach some conclusions. But it's too simple to satisfy somebody working with EEG, for example, or MEG. Okay, so ours is like Professor Baker's from Newcastle. So things coming down in an oscillatory manner in the pyramidal tract. So it's just one little step, and it's just a proposal.
Can you explain just one more time that? So why is Farina's model wrong?
No, it's not wrong. What we discovered is that we have this model going from 2008, more or less, from an older PhD student of mine, Rogério Cisi, and we tried to really take all the Robert Burke from NIH data, Fleshman, and so we tried to really model. Of course, we didn't have human data. We used cat data. So we have all the recruitment, and so many things fit pretty well. Apparently, what they did is most of their motor neurons are already recruited. So there's no recruitment whenever you apply your inputs. So in that situation, apparently, really you don't have this demodulatory effect. But recruitment is very important for fourth generation, as everybody knows. So at least in the range where you have recruitment, this is a possible mechanism for beta oscillations to have effects on force control. So these other groups like Stegeman from Holland and Lowry from Ireland, there are some other groups who have done this and reached the linearity conclusion. But all these works have almost no recruitment at all, probably a few, no recruitment. So it's all motor neurons already discharging. And then you put whatever in the input, and the output force more or less follows what you put as a common input. So the big difference was really modeling correctly, as I think, all the recruitment of the motor neuron pool.
Is there any role for any of the bands and beta?
Oh yeah, we try. You can find this at gamma band also. So there's no restriction. We changed lots of stuff. So we put Rancho cell recurrent inhibition. We put dendritic active dendrites in the motor neurons. So nothing changed this overall thing. So apparently it's pretty robust. So I apologize. It's not didactic, so it was very sorry.
Very nice model. So Andrea, more questions? Do we have more questions from the internet? No, just Mochizuki questions. Okay, so I'm very happy with the results we achieved today.
Well, I thank very much, Luis, for this opportunity and for your attention, or for your patience. And I hope something comes out from this. And I think with Luis, we did a very nice work on light touch. And let's keep talking, because I think we have more things in common that we think, I guess.
Yes, I'm sure we can find some points of convergence to make some studies together. And I think it was quite productive today. The whole day, indeed. We start in the morning with a closed meeting, and now extending for an open meeting, and I'm really happy with the results, and I think we achieved our aim of prospecting, knowing what the state of the art, about what we are doing, and mainly the possibilities for future collaborations. So thank you for coming and for allowing for this opportunity for meeting this group of people. So I thank you all for coming also. And so we are finishing. Thank you very much.